So this is the fourth video that I've made for Unit 9, and I want to talk a little bit about vapor pressure and just that changes of state, in particular between the liquid and the gas, and some of the relationships that we see there. Um, First of all, just to make sure that we've got all our definitions here, vaporization is obviously evaporation. Same thing, it's just the process of a liquid going to a gas. It is an endothermic process because we have to put energy into separating the intermolecular forces between molecules. So, for example, if we were evaporating water, we would have to pull apart water from its other water friends, and depending on how strong those intermolecular forces are, vaporization can be very endothermic or a little endothermic. But it really has to do with how strong those intermolecular forces are. How well do the liquid molecules stick together? So the energy that it takes to do this can be called the heat of vaporization or the enthalpy of vaporization. And it's always going to be represented with this change in H with a lower subscript of VAP. And each substance has its own heat of vaporization. The amount of energy that it takes to go ahead and do that to a liquid. And then there's the reverse process. So if we take a gas and we take it to a liquid, we get condensation. Now, the heat of condensation is the exact same magnitude that we would see for heat of vaporization of whatever that substance is, except that it would be exothermic. So whatever energy you put into vaporizing something, you would get that energy back as the heat of condensation. So the process of vaporization, we could put, say, water into a flask and put a cap on it. And initially what's going to happen are there'll be some random kinetic energy in the water molecules down here, and occasionally there'll be just enough kinetic energy that they'll break free from these intermolecular forces within the liquid. So a couple here, a couple there, and sooner or later we have water molecules that are moving in the gaseous phase up above the surface of the liquid. So some of the liquid will evaporate up into there. But once the air above the liquid gets full, some of those some of those water vapor molecules will go back into the liquid. And so we have this constant exchange now. Some are escaping, some are coming down. So we have definitely this cyclical process that's happening here. Now, the same water vapor molecules will not always exist in the vapor above or in the space above because they're always exchanging places. Some are always evaporating and some of them are always condensing. So we have this constant battle kind of going on. If you were to look at a graph, and the book gave this to us, then the second I put that stopper on the flask, this is when the time starts across the x-axis. And we see that the rate of evaporation starts right off the bat. And the rate of condensation doesn't really start until there's actually some water molecules in there to start returning to the liquid state. And when the rate of evaporation equals the rate of condensation, then at this point right here in the graph, this is when I have what's called an equilibrium, or in other words, a constant amount of vapor that will be in that space above the liquid at all times. So we've talked about this in other contexts. We talked about this in Unit 5 when we were collecting a gas over water. If you remember, we heated a substance and then we caught the gas in a pneumatic tube in the water in the containers. And when we did that, we actually had to subtract out the water vapor from our measurements because there was water vapor in there. And that's exactly what had happened in that tube when we were doing that experiment. So the vapor pressure of water, it doesn't always have to be water, is what I'm getting at. There can be a vapor pressure of any liquid that we have. And even solids have vapor pressure, just not a whole lot of it, typically. But a simple barometer can actually help us measure how much vapor pressure something has. And again, we've seen something like this. This is a simple barometer. We saw these back in Unit 5. And so you would take liquid mercury in a tube, fill it all the way up, Put your thumb on it, turn it upside down, and put it into this bowl of mercury. And just from the mass and the density of the mercury, it's going to come down a little bit, right? It's going to leave this vacuum up here. Now, if I did that to made 3 other simple barometers, I could then inject water, say, at the bottom of this tube. And because water is less dense than mercury, it's going to float all the way up here to my vacuum area. And it's going to change the space, the amount of space that I have up here. I could do this again with an alcohol. I could inject my alcohol down here at the bottom, and again, it would float up to the top of the mercury. And then I could do it to this other molecule here. And if you notice, I've got 3 different amounts of space that are up here. And that tells me a lot about how much vapor these things would produce, each of these molecules would produce. But what I want you to see is the least amount of vapor pressure is happening from something that has really strong intermolecular forces. My water right here has not only a dipole-dipole interaction, but it also has double hydrogen bonding. So there isn't a whole lot of vapor pressure. I have an alcohol here, which has an OH, that hook that we talked about right here. And this gives it some hydrogen bonding. It's a little bigger than water, so it's not going to have as good a hydrogen bonding. But I have a little bit more vapor here. Now I'm looking at this guy right here, and that oxygen, by the way, is not bonded directly to a hydrogen, so I have no hydrogen bonding in this. It's probably polar with the oxygen on the end. So I see a lot more vapor pressure that this thing will produce. So the relationship that I want you to notice here, and I'm going to kind of fast forward over a couple of slides that I would encourage you to go back and look at just to make sure you've got your notes filled out. But what I want you to see is something that has really strong intermolecular forces will produce less vapor pressure. So I want you to think about this. So the stronger they stick together in the liquid phase, the harder it is for them to escape. So something that doesn't stick together as well, and I'm over here off to my far right, something that doesn't stick together as well can escape into vapor easier. So I have more vapor pressure with less intermolecular forces and less vapor pressure with more intermolecular forces. So we have an indirect relationship is what I'm getting at. So vapor pressures of liquids vary widely. And again, anything with a high vapor pressure, we actually call volatile. Most people think volatility is it's going to explode. Well, it could if the vapor it's producing is flammable. But if something produces lots of vapor, then that's what we call volatile. In other words, it evaporates rapidly in any kind of open container. So here's what I want you to make sure that you have summarized here. Liquids with strong molecular forces have low vapor pressure. It's harder for them to escape into the vapor phase. If they have very weak intermolecular forces, they evaporate readily. Okay, so you should at this point be able to look at the intermolecular forces of your solids or your covalent or molecular solids and think to yourself, okay, this one's going to evaporate readily because it has weak forces, so it probably has a low boiling point. Or you could look at that and say, I notice in this molecule that it has hydrogen bonding or strong intermolecular forces, which means it's going to have low vapor pressure and a high boiling point. So just to make sure that you've got some of these relationships down. So as I increase the temperature of any liquid, the vapor pressure is going to increase also. In fact, it increases exponentially. So the more temperature I give it, the more kinetic energy I give it, and the more it may have the ability to get that random energy, kinetic energy, to actually leave the liquid phase. So in your book, they had a table of some vapor pressures for water as a function of temperature. So you can look up, we're going up by 10, 20, 25, 30, 40. But you can look at some of the really big jumps that we start to see as we start giving the water more kinetic energy or more temperature. We also see that in a graph we see this exponential leap that's really happening at all of our substances, water, ethanol, and diethyl ether, the three that we saw in the barometer. Huge changes as we increase just incrementally in temperature. Now, there is a way to calculate this. We have a vapor pressure equation. This is the natural log of vapor at temperature 1 and vapor at temperature 2. We're just making a relationship here between this is the pressure at this temperature and this is the pressure at this temperature. R is the constant. It is what we stored as K in our calculators. But if you look at the units, when we're looking at energy at the top of our fraction here, it only makes sense that our R constant would have joules in it. So just kind of pay attention to that. This equation is pretty straightforward. It's kind of a plug and chug, if you will. Oftentimes they'll say, what is the vapor pressure at this temperature, given that you know the pressure at this temperature. Things to keep in mind. Your constant has a joule in it, and heat of vaporizations are commonly given to you in kilojoules, which means you've got to do a little conversion here. I highly recommend that you just convert your heat of vaporization from kilojoules to joules. That way your joules cross out with your R. I do have an example problem for you, and a couple of them actually. So if you were to use this graph right here, determine whether water, diethyl ether, or has a larger enthalpy of vaporization. Okay, so if you look at, here's diethyl ether and here's water, and we can just see our pressure right here off to the Y and our temperature over here on the X. So the larger enthalpy of vaporization, this is basically how much heat is it going to take to vaporize it? So I can see right here, this one right here, my diethyl ether, it's turning into a gas phase far easier and far quicker than water is. So the smaller slope would have a larger vaporization. In other words, it's going to be pretty easy for me to vaporize this guy right here. We can see that we're breaking those intermolecular forces pretty quickly as temperature goes up, whereas water right here is not. Now, since we know at 760 torr right here is atmospheric pressure, we could also draw a line here. And because at atmospheric pressure, we would say that this temperature is our normal boiling point. So when I say normal boiling point, I mean, what do we normally see it boiling at 1 atmosphere? We normally think of normal boiling point as, oh, well, it's 100 degrees for water. That's the normal boiling point. Normal means at atmospheric pressure. So the normal boiling point of diethyl ether is 34.6, whereas over here, the normal boiling point for water is 100 degrees. Okay, so it's actually based on pressure, not temperature. The other example problem I have here, and this is going to be using your equation here. So if I were to copy this over and put it in here, okay, this is how you're going to solve this problem. You're going to put these in Kelvin. You can leave the pressure in torr if you want, because it's just a relationship here. Just know that when you solve for the vapor pressure at 50 degrees, you're going to have it in torr. So if you switch it to atmosphere, then your answer will be an atmosphere. It's pretty straightforward. So I would encourage you to pause this video just for a second and see what answer you get, and try it again if you don't get 93.7 torr. Okay. There are a couple other things about vapor pressure that I'd like to mention before I close this video out. Going back to this equation right here, oftentimes you may get a practice problem that only gives you, and it's suspicious because it looks like it's giving you really not enough information. And it's probably about water, and it'll say, what is the vapor pressure of water at 25 degrees? And you're thinking, well, I need 2 sets of information to solve this. And what they're expecting you to know is that I have a vapor pressure of 1 atmosphere when water boils at 100 degrees. So you automatically know one of these relationships. So you don't have to be given it in the problem to be able to solve it. So let me say that again. At 100 degrees, you know the vapor pressure of water is going to be 1 atmosphere because that's when it boils. That's when all of it, all the vapor pressure pushes against the atmosphere and it changes states. So one more time. When atmospheric pressure is pushing down on the liquid and the vapor pressure is pushing back on it with the same pressure, 1 atmosphere pushing down, 1 atmosphere of vapor pressure pushing up, then it changes state. And that's when we get boiling point. So I'm going to close this video on that note. Please, by all means, if you have any questions, need some more explanation, you know where to find me. Take care.